Okay, so we're going to get started here on part 1 of IS number 21, again about a difference in two means. We're going to start with confidence intervals for mu1 minus mu2, so the mean for the first group minus the mean for the second group. And I changed the question here. It'll be updated on your notes, but it should say, does caffeine raise your pulse? So here's our situation. Mr. Wilcox's class performed an experiment to investigate whether drinking a caffeinated beverage would increase pulse rates. So I know some of you are struggling with hypothesis test. As I'm reading that, if we were doing a hypothesis test, which we're going to do a confidence interval, but if we were doing a hypothesis test, I would be thinking my alternative hypothesis is going to be greater than whatever value, right? Because increase makes me think it's going to get bigger. Okay, so moving on. So 20 students in the class volunteered. They volunteered to take part in the experiment. But since it's an experiment, we don't necessarily have to have a random sample, right? I was thinking, it's not random, but maybe there'll be randomization somewhere else. So all of the students measured their initial pulse rates in beats per minute. Then Mr. Wilcox randomly assigned the students into groups. So this is where our randomization is going to come. Whenever we have an experiment, we do not necessarily have to have a random sample as long as we have random assignment to the two different treatment groups. So we randomly assigned the students into two groups of 10. Each student in the first group drank 12 ounces of cola with caffeine. So first group got caffeine. Each student in the second group drank 12 ounces of caffeine-free cola. So they got non-caffeinated in the second group. All students then measured their pulse rates again. Okay, so we had an initial pulse rate and then we had a final pulse rate. The table below displays the change in pulse rate. Change in pulse rate for the students in both groups. Okay, so I'm looking at my caffeine group. The first student says 8. Okay, obviously that cannot be their heart rate, I would hope, right? Because 8 beats per minute is like ridiculous, and some of these values are negative. So even if you were thinking like, this is going to be in general a heart rate, hopefully these values are making you think, wait a second, that can't be. So again, when we reread it, it's their change in pulse rate, and they told us how they subtracted. So this is their final pulse rate minus their initial pulse rate. So if these values are positive, that means their pulse rate increased after taking or drinking the cola. So this person increased by 8 beats per minute. This person only increased by 1. This person didn't increase at all. But it does appear that everybody in the caffeine group, at least their heart rate didn't drop, right? There are a couple of zeros, but every other value is positive. When we look at the no caffeine group, some of these are negative. So some of their heart rates did drop over that period of time, or over the period of time where they drank the caffeine-free cola. So what we did here, notice even though they're kind of like stacked on top of each other, these values are not paired together. This student has nothing to do with this student, okay? So these are independent random samples. I shouldn't say independent random samples. They are independent groups, okay? Independent of each other. So what we did is calculate the mean change. We took the average of all these values in the caffeine group, and it was 3.2. And the average of all the non-caffeine group, it was 2.0. So it turns out they both actually had an average increase, but I can tell the average increase for the caffeine group was 1.2 beats per minute higher than the non-caffeine group. Okay, so we're gonna look at the difference in sample means. So just to really highlight this, right? This obviously is not the entire population. This is just a sample of 10 students in each group. So this is the sample mean, right? X bar for the first group, for the caffeine group. And this is the sample mean X bar for the second group. Okay, so I have two sample means and I'm going to subtract them. That will be my statistic. Okay, so let's see what our question says. Construct and interpret a 95% confidence interval for the difference, remember that means we're going to subtract, in true mean change in pulse rate. Notice it says for subjects like these, that's because they volunteered. We cannot generalize to the whole population. It'll just be subjects who are like these students. Who drink caffeine versus who drink no caffeine. Okay, so that's like my whole population. When I finish my sentence, in my conclusion down here, I'm going to include that, okay? So let's describe our parameter. One hint is this mu1 minus mu2. So mu1 would be the true mean for those who drink caffeine minus the true mean for those who do not drink caffeine. So we'll have a difference in true means here. So mu1 minus mu2 is equal to the true difference in the true mean change. And it's a change, let's see, it's a true mean change in pulse rate. I'm getting that from right here. We don't often have a difference of a change, but that's what we've got here, okay? Because we calculated actually their change over that time. Our statistic then, I'm gonna replace mu1 with its sample mean, x1 bar, minus mu2 sample mean, x2 bar, okay? And then I actually should subtract that. So it's going to be 3.2 minus 2.0. And hopefully some of you are asking, how did you know to do to make this one x1 and this one x2, right? Well, the answer is, first of all, caffeine is listed first. Caffeine is listed first, right? That's just a general convention that we're always going to do it that way, but especially when it states it in the question. Sometimes it will specify this is the way you're supposed to subtract. Sometimes it doesn't. Whenever it doesn't specify which way you're going to subtract, in general, we use whichever one is mentioned first as the first group. So we're going to do caffeine minus no caffeine. It is important for us to write down the way that we are subtracting so that someone else who is looking at this would know. Okay, so now we have our caffeine sample mean minus our no caffeine sample mean, and we actually need to write what that is. So 3.2 minus 2.0 is 1.2 beats per minute. Remember to use context. And then we want to state our confidence level, 95%. Okay, so let's move on. We have a name of a procedure. All of our procedures up until this, up until chapter 9, remember, were one sample procedures. And now in section 9.2, when we dealt with two proportions, we had a two sample Z interval or Z test for P1 minus P2 because we were doing a difference in proportions. Now we're doing a difference in independent groups of sample means. So we have a two sample. Since it's means, it's a T interval. And again, it's an interval because we're doing a confidence interval, not a hypothesis test here. For mu1 minus mu2. It's no longer just for mu, it's that difference in means. Okay, so then we have to check the conditions. So the first condition is that we have some sort of random process here. Now, it's not a random sample. We haven't dealt with this, I don't think, to date. We have a random assignment. So I'm going to go back up here where it says randomly assigned. That is what's important. I still get the same effect of having an accurate test because of that random assignment. I just can't generalize it to the whole population because I don't have a random sample. Okay, so that meets my condition. The second condition is the 10% condition, and this is really based on taking a random sample. So whenever we have an experiment, right, and maybe I'll just note that this is because we did an experiment versus a survey, like we would when we would need a random sample, we do not have a random sample to test for the 10% condition. So I don't actually have to do the 10% condition. I'm just gonna cross that one out. I do have to look at that normal condition. So since this is means, there are still three ways to check the conditions. If you remember, there was, let's see, the population distribution could be normal. And in this case, both population distributions would have to be said to be normal. We don't know that, so we move on. We could have n be greater than or equal to 30, then the CLT would apply. Or we could look at the sample distribution and see if they come from approximately normal distributions. Well, unfortunately, our sample sizes are 10 and 10. They are not equal to, or not greater than or equal to 30. So we are gonna have to look at the sample distribution. So when I go to statis.org, I'm gonna show you how to enter the data and look at a histogram real quick to check that the sample distribution shows no strong skew or outlier. I know that it does, so I'm gonna go ahead and write that down just so we have it recorded. show, I should say show, because it's actually two distributions. The sample distributions show no strong skew or outliers. Check. Okay. Actually, I won't check it yet until I actually show you, and then I'll come back and show you when we've approved that. Okay, in the next video, we're actually going to go to StatDisk.